Can you ask again?
So the question was about the axioms and the way you build them. So which one did you came up first with, and how did you build the other one from this first one?
Okay, so so the questions about the postulate is the following. Yeah. So we have the following. First of all, we have to make a formulation of the postulates in a precise setup, namely in a framework. So the framework is that of the operational probabilistic theory. So do you want to know about the framework and then the postulates, or just the postulate without framework is something? So it's like to talk about something without knowing exactly what is the grammar of the language that we are using. Do you understand what I mean?
Maybe then quickly.
So we should. So let's see. Let's start from. It will take maybe 20 minutes, something like that. So with principle and simulation, epistemology, framework. So the framework is the following. So as I said last time, an operational probabilistic theory is a theory which predicts joint probabilities of many events, depending on a set of connections between these events. So we connect events. So now we have joint probability plus the connectivity in defining the framework. So the events are addressed with wires to connect them each other, so they can be more than one, obviously. And there are the so-called, these wires are the so-called systems, as we said last time. And there are the input wires on the left and the output wires on the right. And the marginal probability of some set of events depends, like for example, A, psi, and B, depends also on what we marginalize, on the connection of the marginalized part. This is the philosophy of the operational probabilistic theory. And so the rule of how to connect events are mathematically fit the symmetric strict monoidal braided category. I can tell you very fast. For those that are interested, I can give you maybe something to read if you want. So there are special events. So that since we are addressing a set of events which is bounded, and we connect events, so there are events that have no input because the full graph directed acyclic graph is bounded, and there are events that have no output, and these are what we call observations, those with no output. Can you see my arrow on the screen?
Yes.
And there are those without input that are called preparations. So instead of saying that there is no output and no input, we say there is a trivial input and a trivial output. This makes everything very, very nice. So we have a system which is called the trivial system. The purpose of the theory is to give a mathematical descriptions of the systems and of the probability, mathematical description that allows us to predict the probability distribution of any marginal we want. So we have this rule of sequential composition, and we have the identity event, which is a trivial event, nothing happened, which we designed by a wire. As you see here, this must satisfy an associative rule, and so you may understand that the correspondence with category theory is that the systems work as objects of the theory, of category theory, and the tests or the events work as maps, the morphisms. So with these rules, you have also the parallel composition associations, which defines the composition of systems, and they must be associative. And there is some noise. you have the microphone down, all of you. Okay, and so I was saying the parallel composition must be associative, and associativity actually we define the swap. Let's see, I have to close your face. The swap, which is this crossing of the wire, and and we say that the category theory is symmetric if the swap is an involution, and also the theory, the OPT, is symmetric if the swap is an involution. And then we have otherwise, in the more general case, you have an isomorphism. So just to give an example, we will, in quantum theory, we associate to the system an Hilbert space. So the mathematical description of the system is the Hilbert space. And then the composition comes out to be the tensor product. And the tensor product, you can regard it as a tensor H of A, tensor H of B, equal or isomorphic, if you want, to tensor B, H of B, tensor H of A. So if you exchange the two spaces, is an isomorphism or is an identification. And then you have to require these rules that if you move two events along a swap, they exchange, which is called naturalness. So all these things are so natural that in fact are called naturalness, that people forget they are part of the axiomatization. But the problem is that as long as you work with a theory that you know, everything is fine. But when you start walking in an unknown world of a new theory, where you don't know the mathematical description and you want to derive everything, you have to check all these things. And indeed, in fact, we are addressing many new theories just to understand, for example, the independence of the postulates is something very important. And in order to check that, you need models, theories that satisfy the whole framework, in which for example, all postulates apart from one are true, so that you can understand that that postulate is independent on the other. So when you build a new theory, for example, we build a theory, a classical theory, in the sense that the systems are classical, but the composition of system is not classical. So you may have something like not entanglement, but something similar. And then it is very hard to check, for example, the associativity. You need to do it by the pentagon and the hexagon rule. So, but coming back to what I was saying before. So when is the associativity rule is an isomorphism, we call monoidal the category, and also the OPT. If it's an identification, then it's strictly monoidal. I don't know if you know these things, maybe we are wasting our time. Okay.
I'm familiar with most of this category theory. So
yeah, everybody is familiar. I'm almost done anyway. So
sorry, we had technical issues, so we missed the last 5 minutes. I'm sorry about that, and so we got,
you missed the last 5 minutes.
Yeah, but don't worry, just keep on, and it's fine.
I can put the actually I will do it. I will put the recording on YouTube.
Yeah.
Sorry. Okay. So the OPT is a strict monoidal braided category. So here we have the identification, and the quantum theory is also a symmetric category. So it's a symmetric OPT. So we consider the tensor product an identification, not an isomorphism, the exchange. So I was saying that if, to check associativity, you need to check the pentagon rule, and with the swap also the hexagon rules. I don't know, for people that are familiar with this. Anyway, don't forget, everything is natural. It becomes strictly mathematical if you really want to build up a new theory. For example, for the purpose of understanding independence of postulates. But for quantum theory, everything is obvious because you already know the theory. So this is the other naturalized condition, that you have the parallel composition and the sequential composition commute. This is another assumption that you have to check. So when you build a new theory, you have to check this. And then you have a final description for, so if you want to, the good thing of the OPT approach is that it's a kind of black box approach. So you can describe this full transformation without knowing the details of the transformation, or if you know the details of the transformation, you can build up the full description of the overall transformation. And this is the way in which we address quantum field theory. So we have an infinite directed acyclic graph, which is not bounded, with a with a set of rules, additional rules. But this has to do with quantum field theory. This is a different kind of question. Now we go to the question. First of all, what is quantum theory? As an OPT, I have just to prove that what is associated to the system as a mathematical description, and this is an Hilbert space. The composition, which is the tensor product, as I say, and then the transformation. What are the transformations? So I have events, then I take the equivalence classes of all possible events occurring with the same probability in the same circuit. And I call this transformation. Because I need to consider all, there is no assumption about the theory in general. So what matters, so I don't have the description of the transformation in terms of what is physically. I just want to have a mathematical description of events that I don't know what they are from the point of view of the theory, because I am building the theory, right? So so when I build up circuits, I build up always closed circuits, because I'm considering the bounded situation, apart from quantum field theory, where I already assume a theory, which is, for example, quantum theory. And if I want to make another theory for the field theory, that's another story. But if I use quantum theory, I already know the theory that I need to use to make quantum field theory. So the point is that I don't care about what is the event when I describe mathematically, because the only thing that I need is the probability of happening within a circuit. And so I take the equivalence class of all, let's call, physical transformations, which I have defined with the rules of the category theory, over all possible, the equivalence class corresponding to the events that occur with the same probability within the same circuit. And I call this equivalence class a transformation. And in the case of quantum theory, the transformations are described by completely positive trace non-increasing maps, and in infinite dimension from trace class operators to trace class operators. And everything else comes from these three things as a theorem, namely that states are positive operators and effects are traced with positive operators, and partial traces because they depend on the system, and the states are positive operators that are bounded by 1, and the bound of the trace is because the probability of the preparation is bounded by 1, and the trace provide the probability of the preparation. So there is a unified description in terms of just these three things. Everything else is, so this is important for the philosophical discussion. Everything else is not needed. So the transformational unitary is not needed. You can prove a theorem. By the way, you don't need even all the postulates of the quantum theory, but just the purification postulate that says that every transformation can be achieved by a unitary and a von Neumann. But the fact that can be achieved by the unitary and von Dariano or whatever is totally irrelevant. If the fact that it can be does not mean that it is done. So we have a discussion about the fact that unitarity is not required as a postulate. And indeed, if you give up unitarity and purity also, which is, for example, there is this distinction between closed system and open systems. Open system, you don't have purity, the transformation are not unitary, and so. And then there are closed systems. But the point is that you don't know if the systems are closed or not, because you don't know the interaction that are going around. You don't know this situation only when you build it. Otherwise, you don't know. So it is not falsifiable that I have a transformation that is I'm saying a transformation that is probabilistic, and I say, it is achieved by a unitary transformation, because I don't know with what system my system that undergo the transformation is entangled by a unitary. I don't know that. And I cannot falsify which, if I don't know which system is a unitary interacting with. So this is for a discussion about the interpretations that are all interpretation of something which is additional to the theory, which is not needed, like unitarity and purity. And essentially, this theory is more is closer to GFW than you can imagine, because it essentially takes
the same thing among us. We were chatting and we arrived at the same conclusion.
Yeah, it's closer in the sense that you need to do a GFW theory from the scratch. And anyway, let's go on. I think you understand very simply that once I have these three ingredients, I have everything else, right? So the states is a special case of transformation. Is a transformation for the trivial system. So, for example, what is the trivial system? Just to have a little bit of confidence about what we are saying. The trivial system corresponds to the Hilbert space, which is C. So if I make the tensor product of an Hilbert space with C, I get the same Hilbert space, just to have an idea. And what is a positive operator? Is a completely positive map, trivially, from the Hilbert space C, namely from number, just numbers, to Hilbert space HA. Positive operators means just a completely positive map from C to HA, which preserve the trace is smaller than 1, which is the case that the normalization of the state. Actually, we have this historical rule that we need to normalize states. That's wrong. It's completely wrong, because it is convenient to keep the trace of the positive operator with an additional information inside, which is the probability of preparation. And so everything becomes much easier, and there is a mathematical synthesis. But anyway, let's go to the principles, the postulates, which was the question. So the postulates are these three one. This is sorry. This 6-1: causality, local discriminability, purification, atomicity of composition, perfect distinguishability, lossless compressibility. And there is actually one chapter of the book for each postulate in the beginner part, and then in the second part, which is pretty long, there is the derivation of the theory from these 6 postulates. Let's see the postulates just. So here, the first one is causality, that I've already mentioned to you last time in the first talk. which is the following. So as I said, I can compose transformation. So I can compose transformation in parallel and in sequence. And here there is a preparation, which is the equivalence class is a state. There is a state followed by two parallel transformations that make a transformation. And this overall is a transformation from nothing, from the trivial system, to a system which is the parallel composition of B, F, L, and P. So this is a state. Overall is a state. So a transformation, if a state is followed by transformation, is a state, and an observation with in front preceded by transformation is a new observation. So every closed circuit can be divided into two parts, a transformation and an observation. So the statement of the principle is that the probability of preparations is independent on the choice of observations. So as a rule, we know that the probability of the marginal probability of the preparation should depend also on the other part of the circuit that I marginalized, which is the observation. But if it is a preparation, no, it does not depend. Whereas reversely, the probability of observation generally depends on the preparation. This is the causality principle, which is actually, by the way, very close to the usual meaning of causality. And we can discuss on this for a lot of time. And this is very interesting, by the way, because causality is a huge chapter in philosophy. And so let's go.
Paolo, sorry if I jump in. So there was actually a question on causality. So maybe can you do you mind if I ask Cyril to ask you the question, and so maybe you can?
Sure. No, from now you can interrupt everywhere, because we can spend the time that we want on the principles.
Okay, cool. So I think so now we can focus on one, and
yes.
So on causality. Cyril, a question.
Yes.
So do you want to move on the question with causality?
Yes.
Yeah, I think,
but
yeah.
I think Leah will still wait for an answer. So I don't want to.
So you already have the answer?
Should we maybe give the answer to Leah and then come back to this? Because that will take us on another issue.
So as you prefer, either you, I was thinking maybe since we might focus on each principle, I thought that was basically what Dariano had in mind.
But I didn't finish. I didn't finish causality. Maybe I just a few minutes, a couple of minutes. I finish causality, and then
my bad. Keep on, and then we go back to causality.
So the definition is the one that I gave you. But there are the if and only if condition for a theory to satisfy causality, and one is that the deterministic effect is unique. Which means that if I take a test, which is a collection of transformation that occur overall with probability 1, so I perform the test and I don't know the result, so I sum overall possible events. I get an event which occurs with probability 1, which is deterministic. So by definition. So deterministic event is one, it depends only on the systems. This means that if I change, so if I consider the marginal probability of this preparation, this is independent on the observation. When I say it's independent, because I marginalize the observation. So marginalize means I sum overall possible outcome. So what I got the deterministic event corresponding to the all tests here. And the fact that it is independent on what I have here is equivalent to say that the deterministic event is unique. So we have something, by the way, that has been taken by the Bob Cook group in Oxford as a definition of a causality, by the way. I'm saying they copied from us. Anyway, and the fact that the deterministic event is the trace, over the system's Hilbert space. This is what's come out. And so the states are normalizable is another if and only if condition. So if you have a state which occurs with probability P, there exists always a state which has the same marginal probability distribution. Sorry. Oh my God.
Automatically updated.
I need to cancel this. Sorry. I was saying the probability, they are normalizable in the sense there is always a state which is just, which is deterministic. For every state, there is always a deterministic state, which is just the state divided by its probability of occurrence, which occurs with probability 1. So this means that you are able to prepare always a state, because even though there is a probability which is smaller than 1 to prepare it, you do it many times, and when you get it, you select it. You cannot do such a thing in a theory without causality. So if you have a theory without causality, there are states that you cannot prepare with, because there is no rule, there is no post-selection. I don't know if you have the notion of post-selection is very common in physics. So you cannot just try to prepare, and when you get it, then you use it. It's like, in this case, you have probability, you got it, even though it takes time, but you got it anyway. You cannot do post-selection if you don't have causality. There are many things that you cannot do without causality. To me, causality is important also epistemologically, because actually all these principles have an epistemological content, and because if you make an experiment and somebody can from the future, because here then we have the arrow time corresponding to the input-output arrow. You have an influence coming from the future. You cannot control your experimental setup. You cannot control your experiment. Instead, there is an impossibility of entering in your experiment for using the causality principles if you do it sufficiently fast. So causality is actually something which, if you live without, you have trouble in doing falsification of the theory, because you can never know if something is falsified or comes from the future. It's something, this is my way of looking at it. Anyway, there are many consequences of causalities, especially from the point of view of how the theory is done. For example, you can define the marginal state that otherwise you cannot, because you take the partial trace of a state, means that you are ignoring one thing that, so you can normalize the state is something that you can do it only in the sense that you can make every state deterministic, is something that you can do it only if you have causality. And the fact that the states are normalizable is a consequence, and also not just a consequence, is equivalent to causality. And causality is also provides the convex structure of the theory in terms of convex cones for states, and the intersection of two cones like a splinter for effects, for observations.
So, sorry. I'm seeing your Zoom page, not the slides, I guess.
You are not. Oh, really?
Is it just me?
Yeah, no, we don't. I can't see the slide either.
Oh, that's strange. But everybody else also?
Same here. I thought it was
So
loading.
Now
but
you see my mail or not?
I just see the Zoom. Maybe it's just sharing one application, the Zoom one. I don't know.
No, let's see.
So I guess if you go to share, if you go to share screen, you can pick the one.
I do new share. New share. Okay. Back the meeting. Oh my God.
Yeah.
Yeah, now it's
Okay.
working.
But I cannot see. You are seeing, but I cannot.
Ah!
Let me stop sharing. And oh
And
my,
share again.
Now it
this
is
is
your
a new
email.
experience.
We don't know. We know.
Okay, let's do share screen again. And the problem is that, let's see. The problem is that if I want to change the screen sharing, because I can never find the application on my, I have a huge list of applications that are open. I should close everything next time. Let's see. Let's see. You know, I start with one screen and then I change the screen. If it works, it always worked. Share. Okay. Now you see
Sharing.
my finders, right?
Yeah.
Yeah, folders and files. Yeah.
Now I change app and you see my transparencies.
No.
Not
Oh
yet.
my.
Oh, no. This update spoiled everything.
Yeah, the update made the trouble. You cannot see the screen share principles for quantum theory. You cannot see that.
No.
That's very strange.
Yeah.
Yesterday evening it worked perfectly. They changed the software. Okay, let's see if I can find my screen on the list. Otherwise, I close everything. Because I don't see the keynote application. I don't see it.
Può scegliere quale.
Sì, certo. Io quello sto cercando di fare.
The problem is that is not on the list of the applications. Oh my God. I tried to close and open the keynote because it is not in the list of applications that I have from Zoom meeting. Okay.
They are forbidding you to use the application.
No, this is horrible. If it's the case, it's a big trouble. Yeah, there is another way I can do that. I can use my iPad connected to the Mac and project from there. Let me try one thing, to close and open Keynote. Okay. Grenoble. Okay. Here, I don't see Keynote anyway. Let me do the following. I start Keynote. Keynote is not on the list of applications that I can share.
Strange.
Which is, but it was the same yesterday. But then I changed the screen myself after sharing. So I share my calendar.
Mauro, the plan B is oh yes.
Yes.
You see it?
Yeah.
Yeah.
Okay. Okay.
Cool.
Nobody move. Nobody move.
Oh my. No, because I share the calendar instead. is a trouble. The big trouble. Okay. Let's go on. Okay. Oh, this is actually. So I was saying that the convex structure of the theory comes from causality, and there is one thing which is interesting. I can prove no signaling without interaction in just by circuit, and this is actually something that. Okay, let me first explain why I can prove that. So I have a preparation which is an entangled state shared by two guys that are using two different transformation over the systems, two measurements over the system, A and B. and they cannot communicate by just sharing an entangled state. They need interaction to communicate. And why they cannot communicate by just sharing a state? Because you can stretch wires, putting an identity, and make one longer than the other, you see. And if you cut the circuit here on the red line, this is a preparation, and this is an observation, and vice versa. This is a preparation, and this is an observation. So, but since the marginal probability of the preparation is independent of the observation, you cannot communicate. Because in this case, if Alice tries to prepare something if Bob tries to prepare something for Alice, it cannot communicate because the preparation is independent of the observation. This seems something trivial, but if you think Nick Herbert, 40 years ago, no, less than 30 years ago, proposed a superluminal communication and makes money from the Pentagon, and this using a scheme like this, using cloning by laser amplification of light, and they got 30 referees to show that it was wrong. Actually, nobody was able to show that it was wrong, because it's a long story. I can tell you if you want, but it's a long story. So the idea of making superluminal instantaneous communication by sharing entanglement is an old idea which never dies, and this is completely crazy because it's against causality, which is also in coincidence with the notion of causality in relativity, by the way. So local discriminability. Can you hear me? Everybody see and hear? Okay.
Yeah.
Yes.
Okay.
Yeah.
Well, very well. So local discriminability. Local discriminability is.
So sorry, may I ask you once more?
Yeah. Okay, let's come back to causality. Right. Yes.
Yeah. So we can do two things. So again, since we are obviously running out of time, maybe if Cyril agrees, we can discuss causality now. And then there was the question on local discriminability, I think. Okay. So maybe we do this. So I'm very sorry to ask you this, to everyone. If we want to spend at least like 45 minutes on the philosophical part, we should try to keep this part shorter. But just.
Okay, so my question about causality was, so indeed, I see that it's one of the main axioms that you consider for the reconstruction of quantum theory. And now we know that there are some processes in quantum theory that don't have a well-defined causal order. An example is the quantum switch.
No, this is not quantum theory. This is not quantum theory.
Okay, so that was my question.
Theory. That is a different theory. This is something that we proposed many years ago, and with Valiron, and
so my question was how do you
Czeslaw Bruckner actually took this as a line of research almost full time in Vienna. But this is a variation of quantum theory. So it seems that causality is so it seems that you can keep atomicity of composition, perfect distinguishability. I think certainly you can keep purification, for example, and give up causality to get another theory. So there is a lot of work going on this direction. But this is not quantum. Quantum theory is causal.
Okay, so that's your answer to my question.
Yeah.
Okay. So how would you call the theory that includes the quantum switch if it's not quantum theory?
So the point is that you can make a quantum switch, but it's a way of cheating because, for example, I don't have here the drawing. You can make a ray of light passing through one passing through two sets of transformation in one order, or with a mirror making pass pass through two different order, the same transformation in a different order. But in this case, you have a system which is not a qubit. You have a system which is a qubit, because there is light with spin up or down, with helicity up or down. So a qubit. So there is a qubit which is also with additional possibility that there is no qubit. So the states are three. There is no qubit, and if there is the qubit, is 0 and 1. You see what I mean? So if you can simulate the possibility of exchanging the causal order, having, for example, two copies of the same transformation, and or having systems that have three states instead of one, of two, and they work only on two states as transformations, and they use the third possibility just for reversing the causal order. So it's a way of cheating. So it's a simulation, not really. Whereas if you give up causality and you build up a completely different theory, then a way to get this is to consider transformations of transformations.
Yeah, supermaps.
Supermaps. And this is actually completely.
If you just drop causality in your list of axioms, do you get the process matrix formalism, or can you manage to get the Hilbert space structure?
I'm not sure. I can tell you that I'm not sure that you can really reconstruct the full theory without causality. I'm not so sure. You should ask this, actually, the person who knows more than me about this thing is Paolo Perinotti, because he's following also this line. I gave up this line.
Okay.
There are too many things to do, actually.
Yeah. Thanks.
Thank you. Other questions?
So yeah, there are a lot of. So there was one from Hippolyte on the no-go theorems.
No-go theorems?
Yeah, yes. My question was, how does the Cohen-Specker theorem or even Bell theorem, how do they incorporate in your information-based principles? Because they are not in the principles. I guess since they are about quantum theory, you already talk about no signaling without interaction, so I guess it's my thing.
Yeah, actually,
but
signaling without interaction.
My question is really centered on contextuality, actually, because.
So your question is, how can I understand non-locality in terms of this framework?
Contextuality.
Contextuality.
Yeah.
Yeah, this actually, contextuality, I never thought about. And actually, not only me, but the whole group, we never thought about, because we never worked by chance on the issue of contextuality, not non-locality. Contextuality. On non-locality, we had something, but that's another story. So there are two different issues: non-locality and contextuality. So about contextuality, we know zero. About non-locality, actually, the non-locality, strictly speaking, in the sense that you cannot have an interpretation which is local realist. This comes from entanglement. If you consider, the point is that here, when you have different systems, the two systems are not necessarily far apart in space. There is no notion of space here. There is no notion of space. So you assume that the two systems are far and out of the theory, because, for example, system A and B can be two modes of the electromagnetic field in the same optical fiber, for example. Or A and B can be the spins of two electrons that are very, very far apart and are entangled, right? So here you get the theory, and then from the theory you get non-locality. But non-locality, you need an additional notion about. I don't know. I have to think about it. It's a very interesting question. It's a very interesting question. Actually, we are, for example, considering now the understanding of these things in terms just operational, without using space. For example, proving that you can build up a theory with classical systems that are, the composition is different that in the classical theory, and you have some kind of non-locality, but it's not really the same. So the point is that's a very interesting question. The point is that we never wrote a paper in which the word non-locality enters with the usual meaning. So we know we can prove in a minute entanglement the existence of entanglement from the purification axiom. So that are not separable states, but they are different. They are not separable.
It's not the same as, yeah.
Yeah, the same notion of entanglement, and maybe one can try to prove without using quantum theory, but using just the notion of entanglement, to prove that there is non-locality. But I'm not so sure, because, for example, non-locality is not completely related just one-to-one to entanglement. No, I remember that Werner wrote a paper where he showed that there are entangled states with non-locality and entangled states without.
Yeah, there are entangled states that cannot violate
Right.
inequality. So.
Right. So this is a very interesting question. We are working exactly on these lines. For example, now we are working on the notion of complementarity independently on the theory. The point is that when you work on these notions without using quantum theory, you don't know anything. You cannot do calculation. You have to prove everything. The little connections must be proved one after the other, and before understanding what is, for example, complementarity, we don't have a definition of complementarity, which is not the case of quantum, right? But Bohr was criticized because it was boring, because it was trying to say things that were beyond the possibility of those ears, in the sense that it was trying to use notions independent from the theory, but which were defined historically by the theory. So if you want to define complementarity, think about, without the theory, to a normal person, you say they cannot be measured the same time, they cannot be, yeah, but what does it mean precisely? So this is the line of the research that I'm following, to have all the notions independent on the theory.
Thank you.
Thanks to you. Your question was very interesting. It is actually the line of research I'm pursuing. There are other questions?
Yeah, there are two more on the technical side. One from Maria on the statistics, and the other one was on the no information without disturbance from Lea. So, yeah.
Okay.
So first, Maria.
Okay, yeah, just I want to understand better how this theory deals with the indistinguishable particles.
Indistinguishable particles. Okay, this is actually not quantum theory. Is a theory which is an hybrid theory. It's both classical and quantum, because there is the superselection rule. So you cannot have superpositions. For example, there are some superpositions that are forbidden. So this corresponds to a kind of classical and quantum together. On the indistinguishability is something which goes beyond quantum theory, comes from quantum field theory. So what we have a complete analysis of the fermionic quantum theory, which is actually a special kind of OPT. But you can build up different fermionic quantum theories. So the one that we already know is actually is one of those two cases. But the point is that this is a field theory. In the way which you imagine fermionic theory is not just a theory of systems, a fermionic system. You consider also as a field theory, right? So this is actually you can extract the so-called quantum theory with the super selection rule, and this actually has been done. And there are, for example, some principles that do not hold. For example, the local discriminability principle does not hold in this fermionic theory that is an OPT that we studied, and it holds a bilocal discriminability. So I can tell you what is local discriminability.
Okay.
So that's another interesting question. Anyway, there is a theory which is called fermionic theory, fermionic quantum theory, which is an OPT, and which describes fermions without field theory.
Mm-hmm.
And this is actually the topic of several papers. If you want, I can give you the papers if you are interested in this. I can tell you that everything holds apart from local discriminability. Which are purification holds, causality holds, atomicity of composition holds. But
Okay.
the only one that does not hold is local discriminability, which intuitively, has to do with the indistinguishability in a sense, right? But indistinguishability is something different in quantum field theory because it's indistinguishability of particles.
Yeah.
And here we don't have particles.
Yeah, of course not. Indeed, my problem maybe is how translate, because
No, the anti-commutation, yeah, you can translate.
Okay.
Anyway, if you're interested in the OPT that is fermionic, I can extract some papers from
Okay. Yeah.
But the anti-commutation of what? Some object you didn't mention, or some object you already mentioned?
No, there is no particle in the OPT.
Yeah, but you said it translates as the anti-commutation.
The anti-commutation is translating in the sense that let me remember something that I did.
Okay.
No, is in terms of which transformations are allowed. So the transformations that are allowed are those that preserve parity. And this actually, you can build up more than one fermionic theory.
Okay, so you have to add, you're saying somehow that you have to add a rule to choose what are the allowed.
Right.
Okay.
Right.
Okay, so it's anyway like also in standard quantum theory is coming from the outside somehow. So you are putting this, and you
yes.
Okay.
You are putting rules that make it fermionic. For example,
like
transformations.
Like we do.
Right.
Standard. Okay.
You have to preserve parity, for example.
Okay. So it's like an extra assumption. No, this was my question. In other words, if already from these 6 principles somehow was arising something.
The interesting thing about local discriminability that is violated, it can be violated, for example, a theory which is very similar to quantum theory is quantum theory on real Hilbert space instead of complex Hilbert spaces. And then it violates local discriminability also this case. And you have bilocal discriminability.
Okay, just I cannot imagine this.
I can tell you next transparency. What is local discriminability?
No, I mean I cannot imagine what is real quantum.
Oh, the real the field.
Yeah, the
quantum
real
theory on the field of, instead of complex, on the field of real. You make superposition with real numbers instead of complex numbers.
Okay.
I'm sorry. No, sorry. We are familiar with this nomenclature, but I forget that not everybody is familiar.
No.
Real quantum theory is not.
It's strange.
Not
To be honest, last week I thought for at least 25 minutes that by real you thought the
Realistic classic. The real one.
No, I get it.
It's quantum theory over the field of reals. Superposition are made with reals instead of complex.
Okay, so we have the question from Leah on no information without disturbance.
Ah, that's very interesting. There is a last paper we did, myself, Tosini, and Perinotti, is on this topic.
So I was wondering, because there are some paper about diffraction-based interaction free measurement, and I was thinking if this contradicts this no signaling without interaction or not.
So you're mentioning a work that I probably don't know, which assesses what?
So it's interaction-free measurements.
Ah, interaction-free measurements. Yeah, I saw this topic many years ago, but I don't remember exactly what it is. The point. Ah, okay. Oh no, now I remember.
My guess is it's about post-selection.
It's about, yes. Okay. It was not interaction free, really. The idea is that.
So the thing was having a bomb that would explode if you send one photon in it, but still be able to know if the bomb was there or not without interacting with it. So not having it explode.
But this paper actually, yes, is the famous bomb that does not explode, but you know that is there. It's not that it. So this was. I remember just one thing. This is a very old work, right? 20 years
I have
ago.
one from 2019.
19? No, it's much older. This is an idea of Zeilinger and other people, which is at least 20 years old.
But I think there are new things about it.
There are new things. No, but these are interpretation of quantum theory. So it's always quantum. What I'm saying is just quantum theory with the interpretation about the system as an object, and that you touch it, you don't touch, and things like that. Anyway, we should analyze it. You should analyze what is the statement, and usually is just a way of looking things in a different way, but it's quantum theory. It's exactly quantum theory. So probably is an interpretation of the. You know, for example, there is a paper by Aronoff and other people recently that appeared on PNAS, PNAS, that says that there is the violation of the pigeonholes principles. That I have two holes. There exist states that if I have two pigeonholes and three particles, there is probability 0 that two particles are in the same hole. Some kind of entangled state of three particles, no? But this is not, this is something funny, like funny is the case of the atomic bomb that does not explode and is touched, you know that is there, even though. This is funny because it's the interpretation of the system as an object, which is not right. There is no object. So my previous talk, I started with at least 7 or 8 arguments about the fact that the interpretation of the system as an object does not work. And indeed, in this case, thinking to this as particles does not work. In fact, the conclusion of the paper to me, is wrong. It says, oh, we need to understand more about space-time. It has nothing to do with space-time. in order to understand space-time, you need to have infinitely many systems. You cannot just do with 3 systems. And so I think these are games that is nice to play, to publish a Nature, like, you know, that everybody can read, but not serious. I'd say not serious from the point of view of building a theory, understanding the theory. You understand an interpretation of the theory, because it is too easy when we speak about quantum theory to confuse the interpretation with the true theory. Who says that if I have a particle in the box, particle not in the box is a good interpretation of a 2-state system?
But who says what's the true theory?
No, there is not true theory. There is just quantum theory. It's the interpretation which is not right.
Yeah, but you're saying you can detach any interpretation from the theory. This is
No. If you interpret the system as an object with property, like a ball, like, then you are in trouble. But if you interpret the system as a connection between events, everything works fine. So it's a matter of interpretation. The problem, the practical problem that I have when I explain these things is that people, everybody, including myself for many years, put on the same level the theory, the way in which has been learned at school, not the way in which has been analyzed later, or that one analyzed himself. They put this together with the interpretation, which is most of the time is interpretation of things that have nothing to do with the theory.
Yeah, but the way you said it, it's like you are detaching the theory from interpretations, right?
The point is that no, I need to.
But if we don't interpret, we have nothing. It's just math, no? You have physical postulates, so you are interpreting the math.
But you can have an interpretation of logic if you want. It's the same thing. You want to interpret logic? Yeah. So there is a ball, there is not a ball. Yes or no, right? But this is not a genuine interpretation of logic.
This is your understanding.
Yes, I'm saying quantum theory is a set of rules to understand. Is a grammar. It does not describe stuff. It describes the grammar of physics, the rules of physics. If you interpret the theory in this way, then as a grammar, the grammar is completely free, right? Interpretation free. What does it mean? A subject, an object, a verb.
If it's a grammar, then you don't have any physical explanation of this grammar. It's just like a phenomenological rules.
No. The point is that if it's the grammar of physics, then you must obey the rules of the grammar. Otherwise, you don't do physics. It's the grammar of physics. So there are rules. And the rules are more general than the rules of mechanics.
Yeah.
But how do we know that these rules are true if we cannot justify them from physical grounds?
No, what I say is that quantum theory goes beyond physics. It's a set of rules that physics must obey. If you want to do quantum gravity, why you want to do quantum gravity? Somebody can say, oh, yes, gravity can be classical, right? And quantum theory is wrong. This is another possibility, say wrong, or you can achieve quantum theory by, for example, Bohm mechanics. By the way, I sympathize with Bohmian because I like the idea, but unfortunately, the point is that Bohmian mechanics can never derive quantum theory as such. It just derives quantum theory of particles, which has more to do with quantum field theory. And the point is that the unpleasant thing is that it cannot derive quantum field theory. So I know that talking about these things for Bohmian and anti-Bohmians becomes a kind of fight. But we are exploring different routes. But anyway, the problem is that it's crucial, the notion of particle in the Bohmian mechanics. But it's a mechanics. This is not quantum mechanics. It's quantum theory, the set of rules about state are positive operators, transformation of CP maps, and you know, the rules of the game that you use in quantum field theory. All the observables are self-adjoint operator. You use these rules everywhere in quantum field theory, and actually the point is that you must derive quantum mechanics from these rules and adding other rules, and this is what we did. So actually there is a huge chapter which is the derivation of quantum field theory, and I can tell you very shortly what is the line of research to get quantum field theory. Up to now we got only free quantum field theory. So we have free quantum field theory from principles. I don't think it's a little result compared to, for example, Bohmian theory, where they cannot do quantum field theory really. I'm saying, or it's so complicated that nobody understands.
When you mean you get quantum field free field theory, you mean you get all the particle spectrum, or what do you mean when you have equations of motion?
No, wait a minute. Nobody ever got the spectrum. This is beyond quantum field theory. It is beyond interacting quantum field theory. The spectrum is something. If I got the spectrum, I would be somewhere else. Enjoying life. No. Say I am enjoying life with you. So no. Quantum field theory in the sense of Weil, Maxwell, and Dirac theories, which make quantum.
Yeah, but
electrodynamics. We don't have the electrodynamics.
But I mean, you get, when you say you get, is like you get principles like you are showing, or you get like the equations of motion?
We recover the equation of motion, and, we have the notion of particles emerging.
Yeah, okay. Nice.
I would have a question on this.
But actually, half of my seminar was prepared on this. So if you want, we can see more in detail how it. Because then you change your mind about many things. Because the particle as an emergent notion is well defined. Mm-hmm. And a particle actually, mathematically, the only definition of particle which has to do with the notion of object is an invariant of the Poincaré group. This is the only one that survived. All the other...
Vincent has a finger there.
Just a small question. When you say that you can recover only free QFT, so how does your program relate to the standard or axiomatic approach or algebraic approach to QFT?
The algebraic approach, it is related actually. There is quite a lot of relation, but the difference is that we start with a denumberable set of quantum systems, and we have quantum field theory emerging as a continuum theory in the limit of small wave vectors. They start with the continuum. And starting with the continuum makes a lot of trouble. And the continuum is not really a scientific motivation, because it is a simplification, somebody says, because the word is continuum is not a good motivation, because we see continuum does not mean that it is continuum. The fact that continuum is more practical is not true, because it's practical for some things, but then you have the renormalization issues and all these problems coming from the continuum. There are so many problems. Using the discrete has been considered by many people in the last century. The point that if you use it in the right way, you can recover exactly the continuous case as the limit of small wave vectors. For the free quantum field theory, by starting by very simple principle, much easier than this. So you add to the principle of quantum theory other 5-6 principles that are just, you can restate all these principles in one word as minimization of the algorithmic complexity of the theory. So you simply take this easiest case for everything and you get free quantum field theory.
But people in the 60s, people like Rudolf Haag, Weizmann, they also started with a few axioms in QFT.
But these axioms were mathematical. I'm saying mathematical.
Not more or not less than yours.
Yeah, you're right. But these axioms here have an operational interpretation. So they are. You can think about what.
They also have a causality.
No, but they start from quantum theory. They start from quantum theory, right?
Yes.
And they restate quantum field theory, but they don't derive it as an information process. So we have completely. So we have changed the paradigm. Instead of being materialistic paradigm, instead of having matter, we have just pure information, which is actually something very natural, because if you think about what is the field? What is the field? The quantum field is the ontology. If you ask a philosopher, he would say the ontology is the quantum field, because the particle is a state of the field. So the field, what is it? It's just something which supports states. So as an information system. So I'm not saying something so original if you think a little bit about. So the idea of Feynman and Wheeler, that physics is made of information, just come from the consideration that the ontology in quantum field theory is the field. And what is the field? It's not matter, because matter is a state.
Yeah, but in a more general notion of matter, you can understand quantum fields as a kind of matter. Yes, I think so.
Yeah, but as a kind, you know, the point is that we want to understand the theory, not just a way of reasoning. So it's not as a kind is not allowed. We want really to know what is the field. If you tell the field is made of matter, you say something which contradicts the theory. The field, what is it? And the field is everything. Is the only thing which exists with supposedly in a theoretical sense, because everything else is a state of. And what is a state? The state is just a set of probability rules. So there is not an interpretation of real stuff, because what is a probability rule? What is real about probability? Even the most realistic case of probability, which is that of Popper, does not work.
I think that it would be, I don't know if you agree, it would be now, maybe it would be great to see this derivation of quantum field theory.
Okay.
Or at least having a flavor of it more quantitative, because now I am very curious. I mean, I think I am starting to understand, but since I don't see it.
Local discriminability is something which has to do with non-locality in a sense. It is the following. So it's something which, if I tell you, looks obvious maybe, but it was not obvious not many years ago. So if I have two joint states that are different, there is always a couple of observations that are local, each one on each system, that allows you to have different probabilities. So you can discriminate the two states using only local observations. Okay, so we were talking about local discriminability.
Yeah, because we were seeing, what I was asking before the crash was that when Ippolita before asked the question about Bell non-locality, and I mean
about non-locality.
Yeah, I had the feeling that in this local discriminability.
Yes, in fact, it is connected, but it is not connected with. It is connected with one side of non-locality, which is the following. So if I have two states, that are entangled, for example, that are bipartite, but in particular, in the case of entangled state, I can assess which state it is by local observations. So for example, so this means that I can make a local tomography of a joint state.
So to get, let's say, something similar to Bell's inequality, we should take this and add the restriction that you should jointly observe locally observe the two parts, and or something that involve both the
you see,
A and B, let's say. Because
the connection with non-locality is not so trivial, because as I mentioned, Werner showed that there are entangled states that where you cannot have a violation of Bell inequalities. So they are actually related, but in not in an easy way. Now here what I say is that although we have entanglement which gives non-locality, and people in the past were saying, "Oh, you scientists are crazy because they are continuing to use the bottom-up approach, where the whole world is entangled and makes no sense, right?" And so they are observing locally a situation which is actually a whole, is not made of parts, because everything is entangled. Yeah, but so this, in some sense, reconciles holism with reductionism, in the sense that even though you have a whole to observe, you can observe it locally. So I can make, for example, you know what is a quantum tomography, for sure, I imagine. I can make quantum tomography using local tomographers and making just communication between the two, but I don't need a joint tomographer for the whole state.
Yeah. No, this is pretty clear. No, I was just thinking about the fact that then you have make the communication between the two, and this is what we.
Sorry, I lost the page. Okay.
Yeah.
So this is local discriminability. Is a crucial thing, for example, to define a transformation as an input-output connection in terms of matrix connecting states with observations. So I can know tomography. I can make a tomography of a transformation by just making all possible input and checking the output. This is crucial because, in general, a transformation is defined by its joint probability in a closed circuit, which is the most general for every possible closed circuit, where usually you have to close the circuit in the most general case with a joint observation. So, but the fact that every joint observation actually can be performed locally, then you can consider all these as an input, and then you recover the usual situation.
I have a small finger there. I think I'm a bit. I think I got what you were saying just now, but then I lost my
connection
when I was considering and reductionism and how they should.
No, in the sense that
so it might be, correct me if I'm wrong. Yeah.
Although you have a reality which is an all, because there is non-local connections between one thing here and one other thing there. Everything is in a joint state. I can anyway observe a joint state by local observation. And this is, I'm saying here in this diagram, I put two of them, but I can put 10, 11, 100, 1 trillion of observation on different systems of the same joint state. So I can observe the universe locally. And this is another epistemological principles, that you can make observation locally, because otherwise, if you cannot do it locally, you cannot do it. So there are some practical issues that are not practical. They theoretical, logical, because if you cannot do something locally, you cannot do it.
I understand that. I just I just worry that there might be so maybe there are two levels of discourse that are not precisely the same as far as I see them. So there is a epistemological level where you might want to say that there is some reduction going on because you start by local observations and then you get to the property of the whole. But if I stay more on the non-epistemological side, which is the one that people were moved by in order to talk about holism in quantum mechanics. So like, some more metaphysical weighted sense of holism, then it's pretty straightforward that holism and reductionism are just incompatible. It doesn't mean that you can't be, epistemologically reductionist. But like, if you take the metaphysical question somehow seriously, the definition of holism is simply that there are properties of the whole that do not supervene on the property of the part. And the definition of reductionism is that every property of a composite system of a whole supervene on the property of the part. So there's just one, they are straightforwardly incompatible. So is it the case that when you talk about holism there, reductionism there, I don't know about holism, you mostly thinking about some epistemological issue? Am I right?
It's an epistemological issue in the sense that I can assess that every property of the whole can be obtained, can be derived from assessing not just one property of the part, but all possible properties of the part. So if I observe carefully the parts, like for example, if I make a tomography, I can know precisely the properties of the whole. So it seems to me that is saying something different.
It seems to me that in this reply you were still using some epistemological notion. How I have access to the property of the whole.
Yeah.
But if the point is,
I have access to the property of the whole.
It's strong to me. It's not clear to me if you can really derive or
I can make tomography, so I can know the state. I can know the joint states, so I can know all possible properties of the two systems A and B by making just local observations. Even though there are properties that are entangled, still I can know that there are properties. I can know that there are properties that are entangled by observing just A and B separately, not jointly. So it is, to me, is a reconciliation with reductionism, because I do everything locally. So reductionism is more than just the locality of the observation. Okay, I agree that the notion of reductionism is different. Is more than that. Is also the approach bottom up, which is reductionist, right? For example.
Well, there is an intertheoretic notion of reduction, and there is an ontological notion of reduction. There are always two different levels. And if you take
it is an epistemological one.
Yeah, that was my point.
Yes.
And then my worry was that we were so when you talk, maybe it might be that when you talk about this reconciliation, you might be conflating ontological holism and epistemological reductionism. That if the reconciliation is between an ontological thesis about holism and an epistemological thesis about reductionism, then it's not a problem. So a lot of holists, quantum holists, might be reductionist in the intertheoretic sense. They might believe that you can derive theoretic.
Let me say, when I make an observation of two systems, I think there is an ontology in the preparation. Somebody prepared that there is a state, but the fact that the notion of states itself in physics, apart from other matter that maybe we can discuss another time, because otherwise the notion of state usually in theoretical physics, the notion of state is an epistemological notion. So I don't need to quote Chris Fuchs for this, but the state is an epistemic state. If you believe that the state exists, you need to know the state. Otherwise, it's just a belief which is not falsifiable. And how can you know the state? There are two ways of knowing. Either you prepare it, and so you know it because you did it, or you need many copies to build up the whole probability rules, because the state is a probability rule, right? And then recover the state in this way, like in tomography. But then you are assuming that there is no cheating in the preparation, because somebody can instead prepare a state by changing the state all the time. So the ontology is something that is not falsifiable. So it's a notion that has nothing to do with the scientific method. So it's a notion which is a practical notion to say, oh, what is the real stuff? Is the field, the ontology is the field, but it's not a notion that has to do with the scientific method, the ontology, right?
No, I agree with that. So on the state thing, I have a small. I don't want to be the only one to talk. Just very quickly just to conclude. I understand what you were saying on the holism reduction. I was just saying that either the two notions are understood both epistemically or both ontologically, in which case it's contradictory to say that they reconcile. And so you don't want to be contradictory, or they are saying, or one is epistemological and one is ontological, in which case they can be reconciled. I agree with you, but then it's not clear to me whether you can you can understand holism in epistemological sense. So
I'm not sure I have understood. So holism holism for you is an ontological notion.
In an epistemological sense, then they are still contradictory.
Okay,
it seems to me that.
Okay. This is just, I'm saying this reconciliation between holism and reduction is just pure parler. Is something simple, just to.
I was really honestly trying to understand.
It's not good for a philosopher. Anyway, this is something I want to discuss with you longer, maybe privately, because it looks interesting.
Yeah. Let's. So we still have questions on the realism stuff.
Yeah. What I'm saying, this naive way of saying things, philosophically naive, is that because there were many people, publishing Ayurveda books and kind of stuff like that, saying, oh, scientists do not understand anything, because we know from quantum theory that the world is holistic, and they still are using particles, observe it locally, and and their scientific method is wrong because nature is holistic. You must have a method which is not bottom up, which is not, because you cannot build something which is holistic. There is a whole. You have to understand the whole as such. So this is, I'm saying, the literature of Ayurveda guys and people like that. Oh, but 20 years ago, it was full of these books in Barnes and Noble.
So I don't know who wants to ask these questions, because 4 people had the same question. I don't know. Hippolyte, you want to start on the? So it was phrased in 2 different ways in your question. So yeah, just as you prefer.
Which question are you talking about?
One on information. And
the one on information. Yeah. So yeah, my question is, so last time you said that quantum theory was a software, not an hardware. You use this before. So my question is, Okay, it's
theory,
about information, but information about what? Information.
Okay, quantum theory is not
there
the
an
software.
observer?
Is the operating system. It's not just any software. Quantum theory
Okay.
is the rules. And information about what? Information about nothing. What is the field? The field is information in the sense that so information is a primary notion. Is not a secondary notion. So the quantum field. What is quantum field? Information about what? About what you see. So for example, I have a screen in front of me, right? What are the bits? The bits are made of matter, but this is just because, you know, I can do the bits in this way, but nature can do the bits in other ways, right? So what does it mean? You need to have a support for the information. Then this is yellow, right? The bit is yellow, but this is not really a fundamental entity because it has a feature. It is yellow. It may be red. So if you have something which is fundamental, you have to explain why is yellow or why is red. If you want really something which is fundamental, it has no color. It has no feature. It is just a bit finish, like the quantum field. The quantum field has no feature.
How do you explain the difference between the pen being red and the pen being yellow?
Sorry, can you repeat?
So you were saying, so this pen is red. The pen in front of me is red, and you're saying that's just information. I am processing information about the pen being red, right? And you're saying the pen could be yellow.
Yeah.
Right.
There are
so
yellow pen and red pen.
Then why am I seeing the red instead of the yellow?
Right.
Why? I don't understand.
Yeah, in fact, there are two different states of the same thing.
Yeah, but they are states of something. They can't be state of themselves.
Yeah, but the something is not colored.
Yeah, okay. I grant you that.
Wait a minute. If it is not colored, it is not hard, it is not soft, it has no property at all. So what is it?
For every property, the pen doesn't have this property. Okay, but then suppose you want to understand why I'm seeing the pen as red and not as yellow.
Okay.
If you don't have properties, then you cannot understand the difference.
No, wait a minute.
It seems
the
very
you want
natural
to relate to something fundamental, not to something that you see. So this is not fundamental. This is made of atoms, right?
We agree on that.
Okay. The point is that the color, it comes from the interaction with light, right? Of the matter with light. Matter is made of what? Is made of atoms. And atoms are made of what? Particles. And particles are what? Which color has a particle? The particle has not a color. There is interaction with the field. Okay, then what is a particle? The particle is the stuff? Is stuff in the usual sense? No, because it's a state of a field. So is a property, is the color, is still a color, is the state of the field.
Suppose I grant you everything. Suppose we got to the bottom. Suppose we get to this like huge set of 0 and 1.
The bottom, okay. Yes.
We get to the bottom. We get to
the bottom is the field. The bottom is the field.
Yeah. Okay. So why is the field such that sometimes the pen is red and sometimes the pen is yellow? What's the reason why?
There's another thing, which is the transformation. You can transform. There are the interactions. So yeah, you are right. I'm saying there is not the only ontology, the field. There are also.
So what I'm saying, let me put it another way. So in order for a statement about the pen, in order for a proposition about the pen to be true, it has to be true about something. So yes. Like I'm saying, the very simpler theory of the truth is simply that for a proposition to be true, it has to correspond to something.
Yeah, but this is a theoretical notion. The field is a theoretical notion. It's not something. So you want to have a theoretical notion corresponding to something. You are a realist.
No, I'm saying that I don't see an argument against realism so far. I just see a way to criticize the idea that something we thought to be fundamental are not fundamental. This part I might be with you, I might follow you, but in order to have an argument against realism, I need something more. I need to, I need to show that I can explain everything with information, for instance.
Yes, I'm saying if you derive quantum field theory from information, you explain everything.
No, you don't explain the truth of the proposition.
No, but the truth of the proposition is logic.
No, the truth is not logic.
No,
the truth is correspondence.
No, the truth. There is no truth in the sense that what I see you in this screen. You are not true. I assume that you are the right guy in front of your screen, but it's not true that I can prove.
But I don't think you wanna be skeptical, right? You don't wanna be skeptical.
No, I want to be scientifically skeptical. Scientifically, I don't want to be realist, because realism is a limitation to the scientific endeavor.
Practical realism maybe, but
practically can be good, but sometimes it's not practical. It becomes unpractical because the theory, to be realist, becomes not efficient, or maybe you need notions that, for example, say you are a realist, then you explain me if I have two magnets and I press against each other, what is in between? It's your problem, not mine. What is in between? It's magnetic field. What is the realism of the magnetic field? Come on.
There is a sense in which it's a problem. Of course, it's a problem. So that's why a lot of people have been trying to. So of course, it's hard to say what the stuff is given quantum phenomena. I agree with that, but I'm not sure whether you are participating to the debate. It looks like you are saying that I don't care about this debate, which is fine. But then I don't understand the realist sense.
No. I care about the debate, and I'm not that I don't care about the debate between realism and anti-realism. My issue is another one, is that I ask you, what is the magnetic field, realistically? So the point is that usually realists accept realism only for quantum theory because it's strange, because they didn't understand. The problem is, what does it mean understanding to me?
Yeah,
but then if I ask them, explain me what is the magnetic field, they have no answer, because there is no realistic interpretation of the magnetic field. Because realism also has a preconcept is the materialist concept, because it's not made of matter, the magnetic field. And then what is it?
You didn't say that it's made of particles as well, photons and stuff?
The static one, particles that are moving between the magnets? No, that's not true. I'm talking about the static magnetic field.
The electromagnetic field.
The electromagnetic field, but the static field. But anyway, explain me what is a photon in terms of a particle which cannot be localized at all.
Indeed, it's like the field. It's like it seems to me that you are saying that the stuff, the ultimate stuff, is the field.
Yes.
And it's exactly like the realistic interpretation of the magnetic field or of the electric field is exactly as abstract and as difficult for me to understand as the field of quantum field theory, but nonetheless is what we have. So this is in my opinion, this is a realistic point of view, because you are not denying reality. You are just saying that the real stuff is the field. That is nothing.
No. I'm not denying
my
reality.
grandmother, but for us it can be okay.
Sorry, maybe there is been a misunderstanding. I believe in reality. The problem is that reality is not what I want it to be. Reality, there is something. reality is defined. Reality is defined only because it's different from my free will. That's all.
Yeah. No,
Something happens which does not depend on my free will. So what you are saying, I know that is not me saying that. So you are real and you are different from me. This is okay. But in order to say that the reality is done the way in which I want to tell with a theory is another thing. I believe in the existence of reality. The system
but
of
do you
reality.
think there is a connection? Do you think there is a connection? Sorry, between. So we agree that there is a reality. Awesome. So now, do you believe that the theory we've been talking about, the grammar, along with the theories that you develop using this grammar, do you think they are connected somehow to the reality?
Yes.
Cool. Then we agree on almost everything.
We agree. On this we agree. The point is that reality is not made of stuff. If you say that these qubits, they are made of what? This question is meaningless. This question is meaningless for me. Like the question that Hippolyte asked me, no? So to me, there is no need of saying what are made of, because they are the ultimate stuff. The qubits.
Yeah, so you're like you like Wheeler, right? It's from bits or stuff like this.
Yes.
Yeah.
Wheeler and Feynman, not only Wheeler. So Feynman was supposed to be Wheeler was the teacher of Feynman. Feynman was supposed to be the best theoretician in the history. No, but for example, if I want to be a little bit crude about, for example, a realistic interpretation, we have a theory which is the bomb theory, which does not work for photons, for example. There is a reason. I remember Rimini was telling me all the time, we cannot cope with relativity, with GLW does not cope with relativity, with relativistic invariance. There is no way. And he said, oh, but all these realistic theories, they cannot describe fields because they cannot describe photons. There is a reason. The photon is different from the electron. The electron has something which resembles a particle, but a photon is just that we force the notion of particle because we can count photons.
Yeah.
So if we can count, but counting is true also for information. So it's not.
But from the point of view of quantum field theory, they are exactly the same statement, right? They are states of the field. So there is no difference in that. It's just the properties of the states that are different. And fundamentally, the mass of the electron would come from the interaction with the Higgs field. So even the electron has no mass.
Yeah,
that's true. The point is that it is not the usual notion of classical particle.
Sure, yeah, it is.
It's better. I'm saying it's good for the electron, a little bit good, not completely, but for the photon, it disappears.
Yeah, it's hard. Yeah, I agree.
So what you say is at the end is like quantum theory is like physics of black boxes, and not physics about whatever could be particle is not defined.
Sorry, can you repeat the sentence?
Would you agree when you say that quantum theory is a grammar of physics? Would you agree with a statement like quantum theory is a physics of black boxes or something like this? Instead of physics about particles, about supposedly stuff that are
quantum theory can be used to describe. You can have a realistic interpretation in some situation, not always, for the notion of system. So I said the system connect events. For example, I have two Stern and Gerlach. I see one is clicking, the other is not. I see, this is what I see. And then I change the direction of the magnetic field in the gradient in the first one, and the other is clicking. Now I imagine with my theory that there is a particle flying in between. So I interpret that the connection between the two things that I really see, because there is nothing that I see in between, is a particle flying between them. But because I connect to things that I see, but I don't see the particle. Now, if I want to realistically describe something that I cannot see by definition, you are welcome. But there is no need, because I don't see. So I want to imagine something. I want to have a description which resembles my imagination, not resemble what I see.
So I have to ask you. I would be happy to keep more, but I think so since I have some responsibility here, I won't say that. So officially, so also tomorrow, if we want to keep on going for other 5-10 minutes, I would be happy.
I need to go to have lunch because
yeah. So don't worry about
but anyway, I am really it is really a pleasure for me to discussing with you, because you are really interested and motivated in understanding, as not many scientists are. So you are the best people to talk with, and so I am always available to continue the discussion whenever you want.
We are more than happy if you want to join us for the next meeting.
Yeah. Thanks.
Yes.
Awesome.
Okay. Thank you.
Well,
thank you.
Sorry for the questions we skipped, but I think we did enough.
No. The questions are the best part of
technical problem.
Thank you.
For the next time, I guess I would like to hear more about this. How do you get the quantum field theory and stuff in a little bit more detail and this sort of.
Yes. This is actually the most.
I think it would be nice
part. Yes.
I don't know. I mean, if other people have stuff to question about these principles and stuff, of course.
Yes, actually, this part is interesting because you see the power of the informational approach.
Yeah.
With here is ideological, it becomes a kind of epistemological, but on the other side, you see that really the information approach is powerful. But there are drawbacks, and then this is a subject that we discuss later.
Sure.
The drawbacks is that you can have the perfect idea, but does not mean that it's easy to calculate. This is something which has nothing to do with the method, with the easiness. The fact that, for example, bomb theory is not easy. It's not easy. So you have a beautiful idea, but does not mean that you do the calculation in an easy way. Can we think that the easy is a principle to follow, to be easy? I don't think so, because our brains are made of history, not made of nature. So I don't know. This is something.
That's a beautiful ending note.
Thank you so much.
Yeah.
Thank you.
Thank you for your time.
If you want the recording of the registration of the talk, I can.
Yeah, I have one very small point. So since Mauro is recording the things, is everyone fine if you put it on his YouTube page?
Yeah.
Is it okay for you?
Yeah, it's okay.
Okay.
So I will send you, or Mauro will send you the link.
I will make the YouTube public, but if people don't know that there is a YouTube, they cannot see. So you must tell.
We can share it on us.
Okay.
Cool. Thank you. Have a nice weekend.
Yeah.
You too. You too.
Bye bye.
Thank you very much. Bye.
Thank you.
Thank you.